So we'll go ahead and do some AP style questions here. So for this question, we have two objects, block 1 and block 2. They're sliding along a horizontal frictionless surface, and they collide here at TC, and this shows their velocities as a function of time. So we see that block 2 was initially traveling at -1, block 1 was initially traveling at 4 meters per second, and then when they collide, they're traveling at a speed of 1 meter per second. So we first want to answer which one has a greater mass and what information indicates this. So if we look, what I would look for is a change in velocity. I see that block 1 undergoes a change of 3 here. Block 2 undergoes a change of 2 meters per second. And so that tells me that because block 2 underwent a smaller change, it must be block 2. So that eliminates A and B. Now the reasons we have here for our choices, number 1, block 2 is at a smaller speed before the collision. That's not a valid reason for why it has a greater momentum. However, this second reason, because the final velocity is closer to the initial of block 2 than the initial of block 1, that's just another way of saying that the change was smaller for block 2. So our answer there is going to be D. Now for the second part, was the following is true about the center of mass of the two-block system. So keep in mind that we have no outside forces acting on this system. It's a level surface. It's frictionless, and so since there are no outside forces, that means the velocity of our center of mass is constant. Okay, so that's going to correspond with answer choice B. The velocity of the center of mass of the system moves at a constant velocity of 1 meter per second because there's no friction. In other words, no outside forces acting on the system. For this problem, we have a situation where a railroad car is coasting down a level track at a speed of v, and snow is going to fall into the back of the car, so there's going to be some amount of mass being added to this car, okay, and it's falling at a constant rate, and so some point later in time we're going to have more mass here for our car, and it's still going to be moving down the track at some new speed, but there's definitely going to be additional mass. The first thing we want to do is we want to explain why the car will slow down in a clear, coherent paragraph length response. So there's a few points that we want to make. The first point that we want to make is that momentum is going to be conserved in the x direction here because there are no outside forces on our system in the x direction. There are some y forces, gravity, the force from the track, but in the x direction there are no outside forces. So the momentum of our system is going to be conserved. As the snow falls into the track, though, the mass of the moving object, in this case the car with the snow on it, is going to increase. And so as the mass of the moving object increases, that means the velocity of it must decrease in order for momentum to be conserved. And that's really the key point. This might be a little bit shorter in terms of a paragraph length response, but you do want to make those key points that momentum is conserved, the mass increases, and therefore the velocity decreases because mass and velocity are inversely proportional. So for part B, we want to figure out what the velocity of the car is going to be after the amount of snow that is accumulated in the car is a mass of m. So we're going to set up conservation of momentum here. So initially we're just going to have the mass of the car, which I'll call object 1. Afterwards, we're going to have the car and the snow combined, so both 1 and 2, their combined masses, times the new final velocity. So initially, it's just going to be m, big M times little v, what we're told as the mass and velocity of the car initially. Afterwards, we're going to have big M plus the little m, including the mass of the snow, times that final velocity. And so we end up getting that the final velocity of the car is going to be mv over m plus little m. So the last question here asks what will happen to the acceleration of the car as snow continues to fall in. So there's two things that are really important to note. Number one, it's important to note this expression here. And what we're going to see is that the velocity is inversely proportional to m, the mass of the snow that's fallen in, right? Big M is just the mass of the cart, so that's going to remain constant. That's not going to change. So velocity is simply inversely proportional to that mass there. The other thing that's important to note is that the snow falls in at a constant rate, meaning the mass that lands in the cart in a given time is constant. Okay, so this mass is going to be directly proportional to the time that passes. So keeping those things in mind, the acceleration of the car is going to decrease as snow continues to fall in. And there's two ways of looking at it. The first is thinking about this graphically, our velocity as a function of time, okay? And keeping in mind that the mass that falls in is directly proportional to the time. As time goes on, okay, and more mass accumulates, your velocity function will look something like this. It's going to be an inverse function. And what we see here is that the slope is going to decrease as time goes on. Okay, and since the slope is decreasing, now it's negative, of course, but it's becoming a smaller and smaller negative number, which means our acceleration, the rate at which we're slowing down, is decreasing. Another way of looking at this is thinking about this proportionally. So after a mass of m, let's say that we have a mass of snow equal to the mass of the cart has fallen in, okay, our velocity is going to be v over 2. After a mass of 2m, so that would be twice as long, our velocity is going to be v over 3. And both of those are just coming from our equation that we have up here. But what we end up seeing is that the change, right, from 0 to the time when m has fallen in, it cuts the velocity in half, decreases it by v over 2. But from m to 2m, which is the same amount of time, it only goes from v over 2 to v over 3. So it's still decreasing, but not nearly as much. And that indicates that our acceleration, the rate at which we're slowing down, is decreasing. For this next problem, we have two boxes. They're initially at rest on a level floor here, connected by a spring. The spring is compressed, and it is released then, sending box A traveling to the right, and box B traveling to the left, and box B eventually goes up this ramp here. So the first thing we want to do is sketch a velocity versus time graph here. And we're only going to sketch it from the time that the boxes are initially at rest until after the collision, or after the explosion, I should say, but before box B goes up the ramp. So I'm going to start here with box A, and I'm going to have a red line representing box A. So box A is initially at rest, and it's going to be at rest for some period of time, so it's just riding that axis. I'll say right here at this point we have our explosion, and the spring sends the boxes in the two directions. So box A is going to accelerate for some period of time while the spring's accelerating it, and then it's going to reach a constant speed and look something like that. So that's box A. Box B is also going to start initially at rest, so also riding that axis. And then it's going to explode and start traveling at some speed. We notice, though, that box A is twice as much mass as B, which means box B is going to be moving faster, specifically twice as fast, although we don't necessarily have to draw this to scale. But it's going to drop down and move twice as fast in the opposite direction. And then it's going to maintain a constant speed as well, because we're only thinking about this portion until it begins going up the ramp. The center of mass I'll draw in green. That initially is 0, and since, because they're both at rest, and since there's no outside forces acting on the system, it's going to remain 0. So that center of mass is not going to change. Even though both boxes are moving, the velocity of the center of mass remains 0. So for part B, we're going to go ahead and derive an expression for the speed of box A after the explosion. And so to do that, I'm going to set up my conservation of momentum. I know that initially my system is at rest, neither box is moving, and afterwards both are moving, so the momentum of the system afterwards is going to be MAVA plus MBVB. I know the mass of box A is twice as much as B, and even though I don't know the mass of B, I can still say 2m for box A times its velocity plus just m for box B times its velocity. I can go ahead and cancel out those m's, and so ultimately I'm looking for A, but I need to first figure out what is the velocity of object B afterwards to be able to finish this. So in order to do that, I'm going to think energy-wise about box B sliding up this ramp here. And I'm going to set up my conservation of energy because it's a frictionless surface as that box slides up the ramp. So I know the energy will be conserved, and I also know the height that B reaches. So initially B has kinetic energy because it's moving, and it ends with gravitational potential energy. So I can say 1/2 mass times the velocity of B squared, this same velocity that I have here, is going to be equal to mgh, the height the object B reaches. Those two mass terms will cancel out, and I can solve for VB. VB is just going to end up being the square root of 2gh. So I can plug that back into my momentum equation, and I get that 0 equals 2VA plus the square root of 2GH. And so when I solve for VA, I get that the velocity of box A after the explosion is going to be equal to negative root 2GH over 2. And the negative just indicates that it's in the opposite direction as the velocity of object B. So for C, I'm asked to figure out the energy stored in the spring here. And so in order to do that, I'm going to think about my conservation of energy for the system as a whole, thinking about that spring potential energy that the system started with, that ultimately became the kinetic energy of the two blocks. So I'm going to say my initial energy was that spring potential energy. We have no work done by non-conservative forces, and that ultimately became the kinetic energy of the two blocks. So that spring potential energy is going to be equal to 1/2 times the mass of object A, which is just 2m, times the velocity of object A squared, plus 1/2 times the mass of B, which is just m, times the velocity of B squared. And now I'm going to take these two terms that I got from part B and substitute those in for the two velocities. So my spring potential energy is going to be 1/2 times 2m times negative root 2GH over 2, that quantity squared, plus 1/2 times m times the square root of 2GH squared. I can go ahead and square both those quantities, and I'm going to do a little simplifying here. Some of those 2's and 1/2's will cancel out, and this just becomes 1 over 2. And so what I ultimately get from my spring potential energy is that spring potential energy is going to be equal to mgh over 2 plus mgh, which really gives me a total of 3/2 mgh. So there's my spring potential energy that was ultimately stored in that spring that got converted to the kinetic energy of the two objects. The next question asks what would happen to the height of B if box A was now bolted to the floor. How would that affect that maximum height of B? And the answer is the maximum height would increase. And the reason is with A bolted to the floor, all of the energy stored in the spring is now going to be transferred into box B because A can't move, okay? So A can't gain any of the kinetic energy like it did in our original situation. And you might be thinking, well, wouldn't the energy not be conserved now? Wouldn't it have less energy? And the answer is no, because even though A is bolted to the floor, okay, and there's that extra force, box A doesn't actually move, and therefore no work can be done on an object that's not moving. So there is no extra work being done. The total energy stays the same for the spring, and all of it's converted to B. Okay, now in this case, momentum's not conserved because that outside force of the bolts holding A to the floor, okay, is an outside force making momentum not conserved. However, energy is still conserved, so B gets more energy and ultimately travels up this ramp to a greater height. For the last part here, we want to know what the new height would be. We're calling that h prime. So I'm going to set up my conservation of energy for the system here. And what changes is we just have the spring potential energy going into the kinetic energy of box B. But that ultimately goes into the potential energy of box B. So I'm just going to skip right to that and ignore that kinetic energy that it has in between. And so I'm going to say that the spring potential energy was 3/2 mgh. So that's going to be equal to the gravitational potential energy of box B, which is just mg, and we're calling this h prime now. So we can cancel out the mg's, and we find that our new height, h prime, is just going to be 3/2 times h, which was our original height. For this one, we have an experimental design question about this new kind of toy ball that's designed to bounce perfectly elastically off of surfaces, meaning there is no energy lost. However, this student hypothesizes that no collision can be perfectly elastic and wants to test the validity of this claim. So we're going to design an experiment to do just that. We have all the equipment that we would typically find in a high school physics laboratory, but what I'm going to think about is the easiest way to measure energy, and that's ultimately what we want to do, is we ultimately want to measure the energy before and after the collision with a hard surface, so we'll say a lab bench or the floor. So the easiest way to measure energy, and this is going to answer question 1, is to measure the height of a ball, both before colliding with the hard surface and after colliding with the hard surface, because that's going to allow me to get my gravitational potential energy And I'm also going to go ahead and measure the mass of the ball. That's the other thing I need if I'm getting gravitational potential energy. I'm thinking about UG equals mgh. The equipment I would use here would just be, I would use a measuring tape, and I would tape it to the wall so that it stays in place, and just use that to measure the height of the ball when I drop it and the height that the ball rebounds to. I'm also going to use a scale, okay, to measure the mass. Procedure-wise, the basic procedure I'm going to do to complete a trial is I'm going to drop the ball from some height, allow it to fall and hit this hard surface like the floor, and then rebound back to some height. And I'm going to measure the initial height and the maximum height when it rebounds back. I'm also going to measure the mass using that scale that I talked about. And I'm going to repeat this procedure multiple times, each time varying the height that I drop it from. So we now have a way of getting the height and the mass, which ultimately is going to allow us to calculate the energy before and after the collision using our equation for gravitational potential energy. And we now want to describe how we represent this in a graph or a table and explain how that representation is going to allow us to determine whether or not the data is consistent with the student's hypothesis. So whether or not the collision is elastic for low speeds, but deviates from being perfectly elastic as the collision speed increases. If it's elastic, it means that the initial energy and the final energy are the same. So what I'm going to do, the easiest way of doing this, is graph the initial energy versus the final energy. So I'm going to calculate the initial and final energy for each trial, and that's going to be my gravitational potential energy each time. And then I'm ultimately going to create a graph here, which has the initial energy on the x-axis and the final energy on the y-axis. And I'm going to look for that relationship. And the key is, if it is a linear relationship with a slope of 1, that's going to indicate that energy is conserved. Okay? If it starts to deviate, if we start to see the slope drop below 1, okay, meaning that the final energy is not increasing as quickly as the initial energy is, that's going to show that the collision is not perfectly elastic anymore and there is some energy being lost in that collision. For part C, it gives us this kind of weird hypothetical situation where a student does this experiment and concludes that something went wrong because the graph or table shows perfectly elastic behavior for low speeds, but appears to violate a basic physics principle for high-speed collisions. And we want to come up with an example of a graph or table that would follow this. I've always found this to be a weird question, but it is an actual AP question, so we'll work through it. So the thing that I would say is easiest is a graph with a slope of greater than 1 for high-speed collisions. And so here we have an example of what that graph would look like. We see it has a slope of 1 initially and then very clearly increases. And we want to talk about what basic physics principle that would be violated. Okay, and so the basic principle that would be violated would be conservation of energy. All right, if that graph has a slope of greater than 1, it would show that the final energy is greater than the initial energy. And so that means that the object would somehow be gaining energy without any seemingly plausible way for work to be done on the object. It would end with more energy than what it started with.